Welcome back. Before we begin this journey through the cosmos, I want you to do something for me. Down in the comments, tell me where you're watching from and what time it is right now. Are you in Seattle at 2 in the morning, Mumbai at noon, São Paulo in the evening? Wherever you are, whatever time it shows on your clock, I want you to forget about it. Let time dissolve. Get comfortable. Relax completely. Because tonight, we're going to explore something so vast, so incomprehensibly large, that human time becomes meaningless. We're going to look at the universe itself. You think you understand how big space is. You don't. You think you grasp what infinity means. You can't. The human mind simply isn't equipped to truly comprehend the scales we're about to discuss. But we're going to try anyway. Over the next while, we're going to examine 50 facts about the universe that will challenge everything you think you know about existence, reality, and your place in the cosmos. Some of these facts will make you feel impossibly small. Others will make you marvel at the fact that you exist at all. So settle in, let your mind wander among the stars, and let's begin. The observable universe is approximately 93 billion light years in diameter. Let that sink in for a moment. Not 93 billion miles, not 93 billion kilometers, 93 billion light years. A single light year is the distance light travels in 1 year, moving at 186,000 miles per second. That's about 6 trillion miles. Now multiply that by 93 billion. The number becomes so large it loses meaning. You can write it down, you can calculate it, but you cannot truly comprehend it. And here's the thing that makes it even more incomprehensible. The observable universe is just the part we can see. The actual universe is almost certainly much, much larger, possibly infinite. We're trapped inside this sphere of visibility, bounded by the speed of light and the age of the universe, and we have no way of knowing what lies beyond. The observable universe is simply the region from which light has had time to reach us since the Big Bang. Beyond that boundary, there could be more galaxies, more stars, more planets, extending forever in all directions. Or there could be something else entirely. We have no way to know. There are more stars in the universe than grains of sand on all the beaches on Earth. This comparison gets repeated often because it's effective at conveying scale, but let's actually think about what it means. Imagine every beach you've ever seen. Now imagine every beach you haven't seen, every coastline, every desert, every sandbox, every individual grain of sand in all of those places. The number is staggering, probably somewhere around 7 quintillion grains, 7 followed by 18 zeros. Now consider that there are an estimated 200 billion to 2 trillion galaxies in the observable universe, each containing millions or billions or even trillions of stars. The total number of stars is somewhere around 1 septillion, 1 followed by 24 zeros. For every grain of sand on Earth, there are roughly 100 stars in the universe, 100 stars for each grain of sand, and around many of those stars, there are likely planets. The universe is not just big, it's big in ways that make the biggest things we know seem infinitesimally small. Light from distant galaxies has been traveling toward us for so long that we're seeing those galaxies as they were billions of years ago. When you look at a galaxy 13 billion light years away, you're not seeing it as it is now. You're seeing it as it was 13 billion years ago when the universe was still young. That galaxy has continued evolving, changing, possibly dying in the time it took its light to reach you. It might not even exist anymore. The image you're seeing is a ghost, an echo from the deep past. When we look at the night sky, we're not seeing the universe as it is. We're seeing the universe as it was, at various different times, depending on the distance of each object we observe. The nearest stars show us the past from a few years ago. Distant galaxies show us the past from billions of years ago. We're looking at a universe that no longer exists, frozen in moments spread across cosmic time. There is no way to see the universe as it is right now. The present moment, everywhere simultaneously, is inaccessible to us. We're trapped in observation of the past, and we always will be. The universe is expanding, and that expansion is accelerating. This isn't just movement through space. The space itself is expanding, stretching, growing larger. Galaxies aren't moving through space away from each other. The space between them is increasing. Imagine dots on a balloon. As you inflate the balloon, the dots move apart, not because they're moving across the balloon's surface, but because the surface itself is expanding. Now imagine that happening in 3 dimensions, everywhere, all the time. The universe is getting bigger, and it's getting bigger faster and faster. We don't know why. The acceleration is attributed to something called dark energy, but dark energy is really just a name for our ignorance. It's a placeholder for whatever is causing this accelerating expansion, and we have no idea what it actually is. What we do know is that this acceleration has profound implications for the future of the universe. Eventually, the expansion will accelerate to the point where galaxies outside our local group will recede from us faster than light can travel. They'll disappear beyond our cosmic horizon, forever unreachable. The universe will become increasingly empty and dark, with each island of galaxies becoming isolated in an expanding void. Most of the universe is missing. At least, that's how it seems from our perspective. When astronomers add up all the matter we can detect, all the stars and planets and gas and dust, it accounts for only about 5% of the total mass energy of the universe. Another 27% is dark matter, which we can't see but know exists because of its gravitational effects. The remaining 68% is dark energy, the mysterious force driving the universe's accelerating expansion. Think about that. 95% of the universe is made of stuff we can't detect directly, can't see, can't touch, and don't understand. Everything we've ever seen or studied, every particle we've detected, every force we've measured, all of it represents just 5% of what's out there. We're like people in a dark room who've managed to illuminate 5% of the space with a dim flashlight, trying to understand the entire room based on that tiny glimpse. The vast majority of reality is hidden from us, detectable only through its indirect effects on the small portion we can observe. If you could travel at the speed of light, you could circle the Earth 7.5 times in 1 second. Light moves at approximately 186,000 miles per second. The Earth's circumference at the equator is about 25,000 miles. Do the math, and light could wrap around our planet 7.5 times in a single second. Now extend that to cosmic distances. Light takes 8 minutes to travel from the sun to Earth. It takes about 4 years to reach the nearest star system, Alpha Centauri. It takes 2.5 million years to reach the Andromeda Galaxy, our nearest large galactic neighbor. And it takes 13 billion years to reach the most distant galaxies we can observe. The speed of light is the universe's speed limit, the fastest anything can travel. And yet, on cosmic scales, light seems absurdly slow. The universe is so large that even traveling at this incredible speed, you couldn't cross it in a human lifetime, or a million human lifetimes, or a billion. The distances are simply too vast. There are potentially more planets in the universe than there are stars. For a long time, we didn't know if planets were common or rare. We knew about the planets in our solar system, but we had no way to detect planets around other stars. That changed in the 1990s with the development of new detection methods. Since then, we've discovered thousands of exoplanets, planets orbiting other stars, and the numbers suggest that planets are actually more common than stars. Most stars appear to have at least one planet, and many have multiple planets. If we extrapolate from the stars we've studied to all the stars in the universe, the number of planets becomes truly staggering. Trillions upon trillions upon trillions of worlds, rocky planets like Earth, gas giants like Jupiter, ice giants, lava worlds, ocean worlds, planets we can't even imagine because they exist under conditions we've never encountered. Most of these planets will never be visited. Most will never even be observed. They'll exist, they'll orbit their stars, they'll possibly host life, and we'll never know about them. The universe is full of worlds, more worlds than we could count in 1,000 lifetimes, and almost all of them are forever beyond our reach. Time moves differently depending on how fast you're moving and how strong the gravity is around you. This isn't science fiction, it's established physics, repeatedly verified through experiment. Time is not a constant, universal thing that flows at the same rate everywhere. It's relative, flexible, variable. If you travel very fast, time slows down for you relative to someone standing still. If you're in a strong gravitational field, time slows down for you relative to someone in a weaker field. GPS satellites have to account for this. They're moving fast and experiencing weaker gravity than we do on Earth's surface, and both of these factors affect how fast time passes for them compared to us. Without relativistic corrections, GPS would accumulate errors of several miles per day. The effect is small at human speeds and in Earth's relatively weak gravity, but it's real and measurable. Near a black hole where gravity becomes extreme, time dilation becomes extreme too. An observer falling toward a black hole would seem to freeze at the event horizon from the perspective of a distant observer, taking infinite time to cross it. But from the falling observer's perspective, they'd cross the event horizon in finite time, experiencing nothing special at that moment. Time is not what we think it is. It's not a river flowing at constant rate. It's something stranger, something that bends and stretches with motion and gravity. The sun accounts for 99.8% of the mass in our solar system. Everything else, all the planets, all the moons, all the asteroids, all the comets, all the dust and gas, all of it together makes up just 0.2%. Jupiter, the largest planet, accounts for most of that remaining mass. The sun is so massive that its gravity dominates the entire solar system, holding everything in orbit around it. And yet, compared to many stars, the sun is unremarkable. It's a medium-sized, middle-aged, yellow dwarf star. There are stars hundreds of times more massive. There are stars thousands of times larger in volume. The largest known star, Stephenson 2-18, has a radius about 2,000 times that of the Sun. If you placed it at the center of our solar system, its surface would extend beyond the orbit of Saturn. These ultramassive stars burn incredibly bright and die incredibly young, existing for only a few million years before ending in spectacular supernova explosions. The Sun, by contrast, will exist for about 10 billion years total. slowly burning through its hydrogen fuel in a stable, steady process. We're fortunate to live around such a stable star. The massive giants that burn so bright would create havoc for any planets in their systems, and their short lives would barely allow time for life to evolve. You are made of star material. This isn't poetic metaphor, it's literal fact. The atoms that make up your body, the carbon, nitrogen, oxygen, phosphorus, and all the others, were forged in the hearts of stars. The hydrogen in your body came from the Big Bang, formed in the first few minutes of the universe's existence. But everything heavier than hydrogen and helium was created later in stellar cores. Stars are nuclear furnaces, fusing lighter elements into heavier ones, releasing tremendous energy in the process. Small stars like the Sun can fuse hydrogen into helium and helium into carbon and oxygen. Larger stars can fuse elements all the way up to iron, but elements heavier than iron require energy input rather than releasing energy, so they're not created in normal stellar fusion. They're created in supernovae, in the violent explosions that mark the deaths of massive stars. In those brief moments of explosive fury, conditions become extreme enough to forge the heaviest elements: the gold in jewelry, the uranium in nuclear fuel, the lead in old pipes. All of it was created in supernova explosions. These newly forged elements are scattered into space by the explosion, mixing with clouds of gas and dust. Eventually, these enriched clouds collapse under their own gravity, forming new stars and planets. The Earth and you are made from the ashes of dead stars. You are the universe experiencing itself, made from cosmic recycling on a scale we can barely comprehend. If you could compress the entire history of the universe into a single year, humans would appear at 11:58 p.m. on December 31st. The universe is about 13.8 billion years old. Modern humans, Homo sapiens, have existed for about 300,000 years. That's roughly 0.002% of the universe's age. On our compressed calendar, the Big Bang happens at midnight on January 1st. The first stars form in mid-January. The Milky Way galaxy forms in mid-March. Our solar system forms in early September. Life on Earth begins in late September. Complex multicellular life doesn't appear until mid-November. Dinosaurs rule the Earth in mid-December and go extinct on December 26th. All of recorded human history, every empire, every war, every achievement, fits into the last few seconds before midnight on December 31st. Agriculture was invented 10 seconds ago. The Roman Empire existed 5 seconds ago. The Industrial Revolution happened less than 1 second ago. On the cosmic timescale, we are incredibly recent, absurdly brief. The universe existed for billions of years without us, and will likely exist for trillions more after we're gone. Black holes can merge and create ripples in space-time. When two black holes spiral toward each other and eventually collide, they create gravitational waves, literal ripples in the fabric of space and time that propagate outward at the speed of light. These waves were predicted by Einstein's theory of general relativity over a century ago, but they weren't detected until 2015, when the LIGO Observatory recorded gravitational waves from two colliding black holes about 1.3 billion light-years away. The merger released more energy in a fraction of a second than all the stars in the observable universe combined emit in that same time. Think about that. Two invisible objects, each containing the mass of dozens of suns compressed into points smaller than cities, spiraled together at substantial fractions of light speed, merged, and released so much energy in gravitational waves that we could detect the ripples in space-time over 1 billion light years away. Space and time literally stretched and compressed as the waves passed through Earth, changing distances by less than the width of a proton, but changing them measurably. We now use gravitational wave astronomy to observe events that would be invisible through conventional telescopes, opening an entirely new window on the universe. There may be a multiverse where every possible outcome of every event happens in some universe. The many worlds interpretation of quantum mechanics suggests that every time a quantum event could go multiple ways. The universe splits into multiple branches, one for each possible outcome. In one universe, you turned left. In another, you turned right. In another, you stood still. The number of universes multiplies with every quantum event, which means constantly, everywhere, always. If this interpretation is correct, there are unimaginably many parallel universes, some almost identical to ours, others radically different. In some, you don't exist. In others, you exist but made different choices. In still others, the fundamental constants of physics are different, leading to universes where stars never form or where atoms can't exist. This isn't science fiction. It's a legitimate interpretation of quantum mechanics proposed by serious physicists. Whether it's correct is another question. We may never know. These other universes, if they exist, would be forever inaccessible to us, forever unobservable. They would exist in a sense, but not in any way we could ever detect or interact with. The cosmic microwave background radiation is the afterglow of the Big Bang. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque, a thick fog of plasma where photons couldn't travel far before scattering off free electrons. After this moment, called recombination, the universe became transparent. The photons that were released at that moment have been traveling through space ever since, stretched by cosmic expansion into microwave wavelengths. These photons fill all of space, coming from every direction, forming a faint glow that permeates the entire universe. This cosmic microwave background, or CMB, is one of the most important discoveries in cosmology. It's a snapshot of the universe when it was just 380,000 years old, still glowing from the heat of its creation. By studying tiny variations in the CMB temperature across the sky, scientists have learned about the universe's age, composition, and geometry. We can see the seeds of all future structure in those tiny temperature fluctuations, the slight overdensities that would eventually grow into galaxies and galaxy clusters. The CMB is our most direct view of the early universe, a fossil record of cosmic infancy. Space is not empty. Even in the deepest voids between galaxy clusters, far from any stars or gas clouds, space contains about 1 atom per cubic meter. That might sound empty, and by human standards it is, but it's not nothing. More importantly, even truly empty space, a perfect vacuum with zero particles, is not actually empty in the quantum sense. The uncertainty principle means that particle-antiparticle pairs constantly pop into existence and annihilate each other on timescales so brief they can't be directly observed. These virtual particles are real enough to have measurable effects, influencing atomic energy levels and other phenomena. Space itself has properties. It can be curved by mass and energy. It can expand. It can vibrate with gravitational waves. Space is not a passive stage where events unfold. It's an active participant in the physics of the universe, a dynamic entity that can do things. If you fell into a black hole, you'd experience spaghettification. This is the actual technical term used by physicists, and it describes exactly what it sounds like. As you approach a black hole, gravity becomes increasingly strong, but more importantly, the difference in gravitational pull between your feet and your head, assuming you're falling feet first, becomes increasingly large. Near the event horizon of a stellar mass black hole, this tidal force would be strong enough to stretch you vertically while compressing you horizontally, elongating you like a noodle. The process would be fatal long before you reached the event horizon itself. For larger black holes, like the supermassive ones at galaxy centers, the tidal forces at the event horizon are actually quite weak, and you could cross the horizon without being torn apart immediately. But once inside, your fate is sealed. You would continue falling toward the singularity at the center, and the tidal forces would eventually spaghettify you before you reached it. From your perspective, the fall from the event horizon to your end would take finite time, probably just a fraction of a second for a stellar mass black hole. But to an outside observer, you would appear to freeze at the event horizon, your image becoming increasingly redshifted and dimmer, but never quite disappearing. The sun is gradually getting brighter, and in about 1 billion years, Earth will become uninhabitable. The sun is currently about halfway through its main sequence lifetime, the stable period where it fuses hydrogen into helium in its core. As it ages, the core becomes denser and hotter, causing the sun to brighten slowly. It's already about 30% brighter than it was when the solar system formed. This brightening will continue, and in roughly 1 billion years, the increased solar radiation will cause Earth's oceans to evaporate. The water vapor will be broken down by ultraviolet radiation, and the hydrogen will escape to space. Earth will become a dead, dry world, more like Venus than like the habitable planet we know. Eventually, in about 5 billion years, the sun will exhaust its core hydrogen and begin fusing hydrogen in a shell around the core. It will swell into a red giant, possibly engulfing Mercury and Venus, and certainly rendering Earth completely uninhabitable if it hasn't already. The sun will then fuse helium into carbon and oxygen, go through a period of instability, shed its outer layers to form a planetary nebula, and finally collapse into a white dwarf. This dead stellar remnant will slowly cool over trillions of years, eventually becoming a cold, dark, black dwarf. Our sun, source of all life on Earth, is on a one-way journey to oblivion, and it will take the inner planets with it. There might be life elsewhere in the universe, but we may never find it. Given the sheer number of planets, it seems statistically unlikely that life exists only on Earth. The conditions that led to life here, liquid water, organic molecules, energy sources, are probably common in the universe. But even if life is common, intelligent life might be rare. And even if intelligent life is common, technological civilizations capable of interstellar communication might be rare or short-lived. This is the Fermi paradox. If intelligent life is common, where is everybody? Why haven't we detected any signals? Why haven't we been visited? Various explanations have been proposed. Maybe interstellar travel is simply too difficult, and civilizations stay confined to their home systems. Maybe technological civilizations destroy themselves shortly after achieving technology capable of interstellar communication. Maybe they're out there but have no interest in contacting us. Maybe we're looking in the wrong way or listening on the wrong frequencies. Maybe intelligence is far rarer than we think, and we're essentially alone in the observable universe. We don't know. What we do know is that the distances are vast, the time scales are enormous, and the likelihood of two civilizations existing at the same time, close enough to communicate with compatible technology and interest in doing so, might be vanishingly small. The coldest place in the universe is on Earth. The cosmic microwave background radiation gives all of space a baseline temperature of about 2.7 Kelvin, or negative 270.4 degrees Celsius. You can't naturally get colder than this in space because this radiation permeates everything. However, in laboratories on Earth, scientists have achieved temperatures far colder than the CMB, a tiny fraction of a degree above absolute zero. The coldest temperatures ever recorded, around 100 picokelvin, were achieved in laboratories studying quantum physics. At these extreme temperatures, matter behaves in exotic ways, forming states like Bose-Einstein condensates, where atoms lose their individual identities and act as a single quantum entity. These laboratory achievements demonstrate a curious fact about the universe. Sometimes the most extreme conditions aren't found in nature, but are created by humans seeking to understand nature's laws. Neutron stars are so dense that a teaspoon of their material would weigh about 1 billion tons. When a massive star goes supernova, its core can collapse into a neutron star, an object so dense that protons and electrons are crushed together to form neutrons. A typical neutron star contains about 1.4 times the mass of the Sun, compressed into a sphere only about 12 miles across. The density is similar to that of an atomic nucleus, which makes sense because a neutron star is essentially one giant nucleus. The gravity at the surface is about 2 billion times stronger than Earth's gravity. If you could stand on a neutron star's surface, which you couldn't because you'd be instantly crushed, you'd weigh about 200 billion times more than you do on Earth. Light is bent so strongly by this gravity that you could potentially see the backside of the neutron star by looking forward as light curves around it. Some neutron stars rotate hundreds of times per second, maintained in this incredible spin by conservation of angular momentum from the original, much larger star. These rapidly rotating neutron stars, called pulsars, emit beams of radiation from their magnetic poles, and when those beams sweep past Earth, we detect them as precisely timed pulses. The universe might be flat. This doesn't mean flat like a pancake. It refers to the geometry of space-time. In a flat universe, parallel lines stay parallel forever. The angles of a triangle add up to 180 degrees, and the rules of Euclidean geometry that you learned in school apply on cosmic scales. A universe can also be positively curved, like a sphere, where parallel lines eventually converge, or negatively curved like a saddle, where parallel lines diverge. The curvature depends on the density of matter and energy in the universe. Measurements of the cosmic microwave background suggest that our universe is either exactly flat or very close to it. A perfectly flat universe is actually a special case, requiring a precise balance of density, and the fact that the universe appears so close to flat is something scientists find intriguing. A flat universe has interesting implications for the future. It means the universe will expand forever, gradually cooling and darkening, eventually reaching a state of maximum entropy called heat death, where no more useful energy remains and no more change is possible. Everything becomes dark, cold, and still. This fate is trillions of years away, but it appears to be where we're headed. Some galaxies are moving away from us faster than the speed of light. This seems to violate relativity, which says nothing can move through space faster than light. But these galaxies aren't moving through space faster than light. Space itself is expanding between us and them, and there's no limit to how fast space can expand. The speed limit applies to motion through space, not to the expansion of space itself. Distant galaxies are being carried away from us by expanding space, and beyond a certain distance, the expansion rate exceeds the speed of light. This creates a cosmic horizon. Galaxies beyond this horizon are forever unreachable. Even if we could travel at the speed of light, we could never reach them because space is expanding faster than we could traverse it. These galaxies are effectively beyond our cosmic boundary, existing but forever unvisitable and eventually unobservable. As the universe continues to expand and the expansion accelerates, more and more galaxies will cross beyond this horizon, disappearing from view. The observable universe will shrink in terms of what we can potentially observe, even though space itself continues to expand. Jupiter protects Earth from asteroid impacts. Jupiter's massive gravity acts like a cosmic vacuum cleaner, attracting and capturing many objects that might otherwise strike the inner planets. When comets and asteroids enter the inner solar system, Jupiter's gravity can deflect them or capture them entirely. The most famous example was Comet Shoemaker-Levy 9, which broke apart and slammed into Jupiter in 1994, creating impact scars visible from Earth. Without Jupiter, Earth would likely experience far more frequent large impacts. This has implications for life. Too many impacts would make it difficult for complex life to evolve, as mass extinctions would occur too frequently for life to diversify. Jupiter's presence has likely contributed to Earth's long-term habitability. However, Jupiter's gravity also occasionally sends objects toward the inner solar system, so it's not purely protective. The net effect, though, appears to be beneficial. The presence of a large outer planet like Jupiter in a solar system might be a factor in determining whether that system can host long-lived biospheres. There are rogue planets drifting through interstellar space untethered to any star. When planetary systems form, gravitational interactions can sometimes eject planets, sending them careening out of their systems into the darkness between stars. These rogue planets, also called orphan planets or nomad planets, wander through the galaxy without a sun to orbit. They're almost impossible to detect because they emit no light of their own and reflect no starlight. We've discovered a few through gravitational microlensing, where a rogue planet passes in front of a distant star and its gravity briefly brightens the star's light. Estimates suggest there might be billions of rogue planets in the Milky Way, possibly outnumbering stars. These worlds are cold and dark, far below the freezing point of water, but some might have subsurface oceans kept liquid by radioactive decay or tidal heating from large moons. Could life exist on a rogue planet? It seems unlikely, but not impossible. Life would need an energy source other than sunlight, but Earth has life in deep ocean vents that never sees the sun, thriving on chemical energy instead. A rogue planet with similar conditions might potentially host simple life. We may never know. The Milky Way and Andromeda galaxies are on a collision course. Andromeda, our nearest large galactic neighbor, is approaching the Milky Way at about 68 miles per second. In about 4.5 billion years, the two galaxies will collide and merge. This sounds catastrophic, but galactic collisions are surprisingly gentle. Stars are so far apart relative to their size that actual collisions between stars are extremely rare, even when two galaxies pass through each other. What happens instead is a complex gravitational dance. The galaxy's shapes distort. Star formation is triggered in gas clouds compressed by the collision. Some stars are flung out into intergalactic space. Eventually, over hundreds of millions of years, the two galaxies merge into a single, larger galaxy, likely an elliptical galaxy that astronomers have preemptively named Milkomeda or Milkdromeda. Our solar system will likely survive the merger intact, though our position within the resulting galaxy might be very different. The night sky will look radically different as the two galaxies interpenetrate, with regions of intense star formation creating brilliant stellar nurseries visible to any observers present. Voyager 1 is now in interstellar space, but it will take tens of thousands of years to reach another star system. Launched in 1977, Voyager 1 is humanity's most distant spacecraft, over 14 billion miles from Earth and continuing to move away. In 2012, it crossed the heliopause, the boundary where the sun's influence gives way to the interstellar medium. It's now traveling through the space between stars, carrying a golden record with sounds and images from Earth, a message in a bottle sent to the cosmos. But interstellar space is vast. Voyager 1 is traveling at about 38,000 miles per hour, fast by human standards, but glacially slow on cosmic scales. In about 40,000 years, it will pass within about 1.6 light years of the star Gliese 445. It won't stop there. It has no means to slow down, and it's not headed there deliberately anyway. It will simply drift past and continue on into the darkness. The Voyager probes will outlast Earth, outlast the sun, potentially drifting through the galaxy for billions of years, silent and dark once their power sources finally fail. They're time capsules, carrying the story of humanity into a future we can't imagine. The largest structure in the universe is the Hercules Corona Borealis Great Wall, a galactic superstructure about 10 billion light years across. This is a massive concentration of galaxies, so large that it challenges our understanding of cosmic structure formation. The universe should be relatively uniform at large scales, but structures this massive seem to contradict that expectation. Observing such a structure also requires looking back billions of years to when the universe was younger. At the scales where these largest structures exist, we're reaching the limits of the observable universe, looking back nearly to the Big Bang itself. The existence of structures this large tells us something about how matter was distributed in the early universe, and how gravity has acted over billions of years to pull that matter together. But it also raises questions about whether our models of cosmic evolution are complete. If you could see all wavelengths of light, the night sky would be brilliant with invisible radiation. Our eyes detect only a narrow slice of the electromagnetic spectrum, what we call visible light. But objects in space emit radiation across the entire spectrum, from radio waves to gamma rays. The sun is bright invisible light, but it also emits ultraviolet, infrared, and other wavelengths we can't see. Many astronomical objects are actually brightest in wavelengths invisible to human eyes. Pulsars beam radio waves. Hot gas around black holes emits X-rays. Dust clouds glow in infrared. The cosmic microwave background fills all of space with microwave radiation. If you could see all of this, the night sky would be ablaze with light, with structures and objects invisible to the naked eye becoming apparent. We've built telescopes that can detect these invisible wavelengths, opening up new views of the universe. Multi-wavelength astronomy reveals phenomena that would be invisible in optical light alone, from the birth of stars hidden in dust clouds to the violent processes near black holes. Saturn's rings are disappearing. Those iconic, beautiful rings are temporary on astronomical timescales. The rings are made of countless chunks of ice and rock, ranging from dust grain-sized to house-sized, all orbiting Saturn in a thin disk. But the rings are slowly falling into Saturn, pulled by gravity and dragged by Saturn's magnetic field. At the current rate, the rings will be gone in perhaps 100 million years, maybe less. We're fortunate to live in an era when Saturn has such spectacular rings. In the distant past, the rings may have been more massive or may not have existed at all. In the distant future, they'll be gone, leaving Saturn ringless, like Uranus and Neptune appear today, though those planets actually do have faint rings. The rings might have formed from a destroyed moon or from comets captured and torn apart by Saturn's gravity. We're not entirely sure of their origin. What we do know is that they're a transient feature, and we're lucky to witness them. Dark matter has never been directly detected, but we know it exists because of its gravitational effects. Galaxies rotate in ways that don't make sense based on the visible matter we can see. The outer regions of galaxies rotate too fast. They should fly apart based on the gravity from visible stars and gas. Something invisible must be providing additional gravity to hold them together. Galaxy clusters show similar behavior. The amount of visible matter can't account for the gravitational effects we observe. When scientists add up all the evidence, from galactic rotation curves to gravitational lensing to the cosmic microwave background, they conclude that about 85% of the matter in the universe is this mysterious dark matter. We don't know what it's made of. It's not made of atoms like ordinary matter. It doesn't interact with light, which is why it's invisible. The leading theory is that dark matter consists of exotic particles that only interact through gravity and possibly through the weak nuclear force, but we haven't detected these particles yet, despite building sensitive detectors deep underground to shield them from interference. Dark matter is one of the biggest mysteries in modern physics, a major component of the universe that we can infer but cannot directly observe. The universe had no oxygen for its first billion years. Oxygen, which makes up about 21% of Earth's atmosphere and which we need to breathe, didn't exist in significant quantities in the early universe. The Big Bang produced hydrogen and helium and trace amounts of lithium, but nothing heavier. Oxygen had to be created in stars through nuclear fusion, then released into space by stellar winds and supernova explosions. But even once oxygen was being produced, it didn't accumulate in planetary atmospheres at first because it readily reacts with other elements, forming compounds like water and iron oxide. On Earth, oxygen levels only increased dramatically about 2.4 billion years ago during the Great Oxidation Event, when photosynthetic bacteria began producing oxygen faster than it could be absorbed by chemical reactions. This oxygen buildup was actually catastrophic for the anaerobic organisms that had dominated Earth until then, representing one of the first major extinction events. But it also paved the way for more complex life forms that could use oxygen to power their metabolism. We are oxygen-breathing organisms on a planet made mostly of elements heavier than helium, living in a universe that spent its first billion years producing only the lightest elements. Everything that makes us possible required stars to live and die, enriching the cosmos with the elements of complexity. Each atom has a history, a journey through the cosmos, from the Big Bang through multiple stars, through the formation of the solar system, through Earth's geological processes, through the biosphere, and eventually into you. You are not separate from the universe. You are the universe, localized, a temporary pattern in the endless dance of atoms through space and time. The Earth's atmosphere is leaking into space. Every day, about 3 kilograms of hydrogen and 50 grams of helium escape Earth's gravity and drift into space. This happens because some molecules in the upper atmosphere move fast enough to exceed Earth's escape velocity. Over Earth's 4.5 billion year history, it has lost significant atmosphere this way. Early Earth had a much thicker atmosphere, including more hydrogen. The loss of hydrogen, particularly from water molecules broken down by ultraviolet radiation, has been significant over geological time. Mars lost most of its atmosphere this way. Being smaller, with weaker gravity, and lacking a protective magnetic field, Mars couldn't hold on to its air. The thin Martian atmosphere we see today is a remnant of what was once much thicker. Earth is large enough and has a strong enough magnetic field to retain most of its atmosphere, but the slow leak continues. In the distant future, billions of years from now, Earth will lose more of its atmosphere, though the sun's evolution will make the planet uninhabitable long before atmospheric loss becomes critical. There's a point in space where our solar system's influence ends and interstellar space begins, but it's not a sharp boundary. The heliosphere, the bubble of charged particles blown out by the solar wind, extends far beyond the orbit of Pluto, but it doesn't have a clear edge. The heliopause, where the solar wind's pressure balances the pressure of the interstellar medium, is a dynamic, fluctuating boundary that moves in and out as the solar wind varies. Beyond this, there's a region where interstellar matter piles up, compressed by its collision with the expanding heliosphere. Voyager 1 crossed the heliopause in 2012, but it's still within the sun's gravitational influence and will be for thousands of years. The true edge of the solar system, if we define it by gravity, might be the Oort cloud, a theoretical sphere of comets extending perhaps halfway to the nearest star. The solar system doesn't end cleanly. It fades gradually, with the sun's influence becoming weaker and weaker until it finally becomes indistinguishable from the general galactic background. Gamma-ray bursts are the brightest events in the universe since the Big Bang. These intense flashes of gamma rays come from collapsing massive stars or from colliding neutron stars. For a few seconds, a gamma-ray burst can outshine the entire rest of the universe in gamma rays. The energy released is staggering, equivalent to converting the mass of several Earths into pure energy. If a gamma-ray burst occurred in our galaxy, pointed at Earth, it could cause a mass extinction. The gamma rays would strip away the ozone layer, exposing life to deadly ultraviolet radiation. Fortunately, gamma-ray bursts are rare, and the chance of one occurring nearby and pointed at us is very small. But it's not zero. Some scientists have speculated that past mass extinctions might have been triggered by gamma-ray bursts, though evidence for this is limited. These events remind us that the universe contains processes of unimaginable violence, and we're fortunate to live in a relatively quiet neighborhood. The cosmic distance ladder is how we measure distances to faraway objects, and it's built on a chain of methods, each calibrating the next. For nearby objects, we use parallax, measuring how a star's position shifts as Earth orbits the sun. For more distant objects, we use standard candles, objects of known brightness. Comparing their apparent brightness to their actual brightness tells us their distance. Cepheid variable stars, which pulsate with periods related to their luminosity, are crucial standard candles. For even greater distances, we use type 1a supernovae, which have consistent peak brightness. Each method extends our reach a bit farther, but this chain of calibrations means that errors propagate, If our nearby measurements are wrong, all the distant measurements built on them are wrong too. The cosmic distance ladder is constantly being refined as we improve our measurements and find new methods. Our understanding of the universe's scale and expansion rate depends on this ladder being accurate. The vacuum of space isn't a perfect vacuum. The interstellar medium contains about 1 atom per cubic centimeter on average, though this varies greatly depending on location. Dense molecular clouds can have millions of atoms per cubic centimeter, while voids between galaxy clusters are much emptier. Even in the emptiest regions of intergalactic space, there's occasional hydrogen, helium, and trace amounts of heavier elements. There are also cosmic rays, high-energy particles zipping through space at near light speed. There are photons from the cosmic microwave background and from distant stars. There are neutrinos, ghostly particles that barely interact with matter, streaming through everything. There's potentially dark matter, invisible but present. True perfect vacuum, with absolutely nothing in it, probably doesn't exist anywhere in the universe. Even the quantum vacuum seethes with virtual particles, as mentioned earlier. Space is not empty. It's just very, very sparse. Magnetars are neutron stars with magnetic fields a quadrillion times stronger than Earth's. These are the strongest magnetic fields known in the universe. A magnetar's magnetic field is so powerful that it distorts the shapes of atoms, turning them into elongated cylinders. If a magnetar came within a few 100,000 miles of Earth, its magnetic field would be strong enough to disrupt electrical activity in our bodies, likely fatally. From a safe distance, a magnetar looks like any other neutron star, a small, dense object. But occasionally, magnetars have starquakes, sudden cracks in their solid crusts caused by magnetic stress. These quakes release enormous amounts of energy, producing flares of X-rays and gamma rays that can be detected across the galaxy. The most powerful magnetar flare ever recorded in December 2004 came from SGR 1806-20, about 50,000 light-years away. The flare briefly ionized Earth's upper atmosphere, even though the magnetar was halfway across the galaxy. If that flare had come from a magnetar just a few dozen light-years away, it could have caused significant damage to life on Earth. The temperature at the core of the Sun is about 15 million degrees Celsius. At these extreme temperatures, hydrogen nuclei collide with enough energy to overcome their electrical repulsion and fuse together, forming helium and releasing energy. This energy works its way outward through the Sun, taking hundreds of thousands of years to travel from the core to the surface. The photons created in fusion reactions in the core scatter countless times as they move outward through the dense solar interior, following a random walk that takes an incredibly long time. By the time energy reaches the Sun's surface and radiates into space as light, the original photons from fusion have been absorbed and re-emitted so many times that they've lost all connection to their origin. The sunlight we see left the Sun's surface about 8 minutes ago, but the energy in that light was created in fusion reactions hundreds of thousands of years ago. The Sun is a vast, slow energy storage device, releasing gradually the energy generated in its core. Proxima Centauri, the closest star to our solar system, is about 4.2 light-years away. This is cosmically close, yet incomprehensibly far by human scales. With current technology, sending a spacecraft to Proxima Centauri would take tens of thousands of years. The fastest spacecraft ever launched, the Parker Solar Probe, travels at speeds up to 430,000 miles per hour at closest approach to the Sun. Even at this incredible speed, it would take thousands of years to reach Proxima Centauri. Proposed future technologies, like light sails pushed by lasers from Earth, could potentially reach a substantial fraction of light speed and make the journey in decades. But even this would require technology far beyond what we currently possess. The distances between stars are simply enormous. Science fiction often glosses over this, imagining faster-than-light travel or wormholes, but the reality is that the stars are separated by gulfs so vast that reaching them remains beyond our capabilities. We are, for now, confined to our tiny corner of the galaxy. The moon is slowly drifting away from Earth at about 1.5 inches per year. This happens because of tidal interactions between Earth and moon. The moon's gravity creates tides in Earth's oceans, and friction from these tides slowly robs Earth of rotational energy. This energy is transferred to the moon's orbit, causing it to gradually spiral outward. In the distant past, the moon was much closer and appeared much larger in the sky. Days were shorter because Earth rotated faster. As the moon continues to drift away, Earth's rotation will continue to slow. Eventually, billions of years in the future, Earth and moon will become tidally locked, with both always showing the same face to each other, just as the moon currently shows the same face to Earth. This process is incredibly slow, but it's measurable. We can detect it by bouncing laser beams off reflectors placed on the moon by Apollo astronauts and measuring the increasing distance. The moon that humanity has watched throughout history is gradually leaving us. Almost every element heavier than iron in your body was created in a supernova or neutron star collision. Elements up to iron can be created in the cores of massive stars through fusion, but elements heavier than iron require energy input rather than releasing energy when formed. They're created in the extreme conditions of supernova explosions or in the collisions of neutron stars, where temperatures and pressures are high enough to drive these endothermic reactions. The gold in jewelry, the platinum in catalytic converters, the uranium in nuclear fuel, all were forged in these violent events. When a neutron star collision occurs, it creates a kilonova, an explosion that briefly outshines an entire galaxy and produces vast quantities of heavy elements. Gravitational wave observatories have now detected several neutron star collisions, and follow-up observations with telescopes have confirmed that these events do indeed produce heavy elements, observationally verifying what had previously been theoretical. You are made of rare materials, forged in the universe's most violent processes. If you were at the North or South Pole, you would see completely different stars than someone at the equator. Earth's spherical shape and rotation create different perspectives on the sky depending on latitude. From the North Pole, you'd see only stars in the northern celestial hemisphere circling endlessly around Polaris, the North Star, never rising or setting. From the equator, you'd see the entire celestial sphere over the course of a night, with stars rising in the east and setting in the west. From the South Pole, you'd see only southern stars, circling around the South Celestial Pole, with no North Star equivalent. This is why different cultures throughout history developed different constellations and different star lore. The Maya saw different patterns than the ancient Greeks. Aboriginal Australians saw stars that never rose above the Mediterranean horizon. The sky you see depends entirely on where you stand on Earth, a reminder that our view of the universe is always limited and local, shaped by our particular position in space and time. The sun loses about 4 million tons of mass every second through nuclear fusion. Einstein's equation, E equals mc squared, tells us that mass and energy are equivalent. When the sun fuses hydrogen into helium, the resulting helium has slightly less mass than the original hydrogen. That missing mass has been converted into energy, the light and heat the sun radiates into space. 4 million tons per second sounds like a lot, but the sun is so massive that it can sustain this loss for billions of years. It's been doing this for about 4.6 billion years and has enough hydrogen fuel to continue for another 5 billion years or so. Despite losing 4 million tons every second, the sun has only lost about 1/20th of 1% of its mass since it formed. The scale of the sun is so large that even enormous losses are sustainable for cosmological timescales. Mass energy conversion powers the stars, and this process, repeated in trillions of stars across billions of years, is what has lit the universe since the first stars formed. Space smells like seared steak, hot metal, and diesel fumes, according to astronauts who've gone on spacewalks. Obviously, you can't smell space directly. There's no air to carry odors, and opening your helmet would be fatal. But astronauts report that when they return to the airlock after a spacewalk, their spacesuits have a distinctive smell that transfers into the air when they remove their helmets. This smell is likely from high-energy particles and radiation in space interacting with the suit materials, creating polycyclic aromatic hydrocarbons and other compounds. It might also come from atomic oxygen, single oxygen atoms created when molecular oxygen in the upper atmosphere is broken apart by solar radiation. These highly reactive atoms bond to whatever they encounter, including spacesuit materials, creating oxidized compounds that have distinct smells. The scent of space is a reminder that space isn't empty. It's a harsh environment full of radiation and reactive particles that interact with anything exposed to them. Brown dwarfs are failed stars, objects too massive to be planets, but not massive enough to sustain hydrogen fusion. They're typically between 13 and 80 times Jupiter's mass. They form like stars from collapsing gas clouds, but they never accumulate enough mass to ignite fusion in their cores. Some brown dwarfs can fuse deuterium, a heavy isotope of hydrogen, but this process is brief and doesn't provide long-term energy like hydrogen fusion in true stars. Brown dwarfs glow dimly from the heat of their formation and from residual energy, but they gradually cool and dim over time. They're difficult to detect because they're so faint. We've discovered hundreds within a few dozen light years of the Sun, and there may be billions in the Milky Way. The nearest known brown dwarf is about 6.5 light years away. Brown dwarfs blur the line between planets and stars, neither one nor the other, existing in a transitional category. They're a reminder that nature doesn't always fit neatly into our classification systems. The Great Attractor is a gravitational anomaly pulling our local group of galaxies, along with hundreds of thousands of other galaxies, toward a specific region of space. It's about 150 to 250 million light years away in the direction of the constellation Centaurus. We can't see the Great Attractor directly because it's behind the zone of avoidance, the region of sky obscured by our own galaxy's disk. But we can detect its gravitational influence. Galaxies in our region of the universe are being pulled toward it at speeds of several hundred kilometers per second. The Great Attractor itself appears to be a massive concentration of galaxies, possibly a supercluster, but the details remain mysterious because of the obscuration. There might be an even larger structure, the Shapley supercluster, pulling everything in that direction. We're falling through space, drawn by invisible hands toward a destination we can barely perceive, a reminder of how much remains hidden and unknown in the universe. If a star passes close to our solar system, it could disrupt the Oort cloud and send comets raining down on the inner planets. The Oort cloud is a theoretical sphere of comets surrounding the solar system at a distance of thousands of astronomical units from the Sun. These comets are loosely bound by the Sun's gravity, and a passing star's gravity could perturb them, sending some into the inner solar system. This might have happened in Earth's past, causing periods of increased comet impacts. Some mass extinctions have been tentatively linked to comet showers, though evidence is debated. The Sun orbits through the Milky Way, passing through regions of varying stellar density. When it passes through denser regions, close stellar encounters become more likely. The next anticipated close approach is Gliese 710, a red dwarf that will pass within about 63,000 astronomical units of the Sun in about 1.3 million years. This is still very far away and unlikely to significantly disturb the Oort cloud, but closer passes have probably occurred in the past and will occur in the future. The solar system is not isolated. It's moving through a galaxy full of other stars, and these stellar neighbors occasionally come close enough to influence us. The cosmic web is the large-scale structure of the universe, a vast network of galaxy filaments separated by enormous voids. Galaxies are not distributed randomly. They're organized into sheets and filaments surrounding vast, empty regions. The filaments, where most galaxies reside, are hundreds of millions of light years long. The voids between them contain few galaxies, just occasional isolated objects in vast, empty space. This structure formed through gravity acting on the slight density variations present in the early universe. Overdense regions attracted more matter, growing denser while underdense regions lost matter to their surroundings, becoming voids. The result is a structure that resembles a sponge or a network, with galaxies outlining the edges of enormous bubbles of empty space. Understanding this structure helps us understand how the universe evolved from the relatively smooth early conditions we see in the cosmic microwave background to the complex structure we observe today. The cosmic web is invisible to the naked eye, only becoming apparent when we map millions of galaxies and look at their distribution on the largest scales. We are living in the stelliferous era of the universe, the age of stars. This era began a few 100 million years after the Big Bang, when the first stars formed, and it will continue for trillions of years as long as there's enough gas to form new stars. But eventually, star formation will end. The universe will enter the degenerate era when the only objects are stellar remnants, white dwarfs, neutron stars, black holes, and brown dwarfs gradually cooling toward absolute zero. This era will last perhaps 10 to the power of 40 years, a 1 followed by 40 zeros, an incomprehensibly long time. After that comes the black hole era, when even the longest-lived stellar remnants have decayed or been consumed by black holes, and the universe consists mainly of black holes slowly evaporating through Hawking radiation. This era lasts until perhaps 10 to the power of 100 years. Finally comes the dark era, when even the black holes have evaporated, leaving only fundamental particles spreading ever farther apart in an expanding, darkening universe. We live at the very beginning of cosmic history, in a bright moment before the long fade into darkness. The stelliferous era is less than 1% of the universe's total timeline. We exist in a brief, brilliant flash at the start of a story that will unfold for timescales that make the current age of the universe seem like an eye blink. And with that perspective, we return to where we began. Here you are, sitting wherever you are, watching this video, made of star material, living on a planet orbiting an ordinary star in an ordinary galaxy among hundreds of billions of galaxies in an observable universe that might be just a tiny fraction of all that exists. You are impossibly small and impossibly important. Small because the universe is vast beyond comprehension, and you occupy an infinitesimal portion of it for an infinitesimal moment. Important because you are the universe's way of knowing itself. You are matter that has become conscious, stardust that has learned to think, atoms that can contemplate their own existence. The universe is 13.8 billion years old. In that time, it has expanded from a hot, dense state to the vast cosmos we observe today. Stars have formed and died. Galaxies have merged and evolved. Planets have condensed from stellar debris. On at least one of those planets, and likely many more, life has emerged. On at least one of those life-bearing worlds, intelligence has developed. And that intelligence has looked up at the night sky and asked questions. Where did we come from? How did all this begin? What does it all mean? We don't have complete answers to these questions. We may never have complete answers. The universe keeps surprising us, revealing new mysteries as we solve old ones. Dark matter, dark energy, the ultimate fate of the cosmos, the possibility of other universes, the nature of consciousness itself, all remain mysterious. But we keep looking, keep questioning, keep learning. That's what makes us human. That's what makes this moment in cosmic history unique, at least in our corner of the universe. Tonight, when you look up at the stars, remember what you've learned. Those points of light are suns, many with their own planets. The darkness between them is not empty, but filled with invisible matter and energy we barely understand. The light reaching your eyes left those stars years or centuries or millennia ago. You're seeing the past, looking back in time, observing a universe that no longer exists in the form you're seeing. And if someone on a planet orbiting one of those stars looks toward our sun, they're seeing our past too, light that left Earth years ago, carrying an image of a world that has already changed. We are all connected through this web of light and time, through the shared origin of our atoms in stellar cores, through the universal laws of physics that govern everything from the smallest particles to the largest structures. We are not separate from the universe. We are part of it, intrinsically and inextricably. When you look at the stars, you're looking at your ancestors, the furnaces that forge the elements in your body. When you contemplate the vastness of space, you're exercising a brain built from cosmic raw materials. When you wonder about the meaning of it all, you're asking the universe to explain itself to itself. Sleep well tonight, under your ceiling or your sky, on your planet that's hurtling through space at hundreds of kilometers per second, in your solar system that's orbiting the galactic center, in your galaxy that's falling toward the great attractor, in your universe that's expanding toward an unknowable future. You are home, and home is moving, falling, expanding, evolving. Nothing is static. Nothing is permanent. The only constant is change, and the only certainty is mystery. The universe is vast, ancient, beautiful, and strange, and you are part of it. Never forget that. You are made of stars, living on a starlit world, looking up at stars, trying to understand stars. You are the universe experiencing itself, one consciousness among potentially countless others, asking the eternal questions, seeking the hidden answers, living briefly in the long story of the cosmos. Rest now and let these thoughts drift through your mind like galaxies through space, distant and beautiful and ultimately mysterious. The universe will still be here tomorrow, still expanding, still evolving, still waiting for minds like yours to observe it and wonder. But before you drift away, there are more secrets to share, more wonders to contemplate. The speed of light isn't just a speed limit, it's the speed of causality itself. Nothing can happen faster than light speed, because light speed is the rate at which cause and effect propagate through the universe. When you flip a light switch, the electromagnetic signal travels down the wire at near light speed. When you see lightning, the light reaches you traveling at light speed, followed by thunder traveling at the much slower speed of sound. Every interaction, every force, every change propagates at light speed or slower. This has profound implications. It means the universe has a built-in delay between cause and effect. It means simultaneity is relative. What's happening now on a distant planet is not a fixed, objective fact, but depends on your reference frame. Two events that appear simultaneous to one observer might occur in sequence to another observer moving at a different velocity. Time and space are woven together into space-time, and the speed of light is the conversion factor between space and time measurements. There are stars so large that if you traveled at the speed of light around their equator, it would take hours to complete one orbit. The largest known stars, hypergiants like Stephenson 2-18 or UY Scuti, have radii roughly 1,500 to 2,000 times that of the Sun. The Sun's radius is about 432,000 miles, so these giants have radii approaching 1 billion miles. To travel around such a star's equator at light speed would take about 7 hours. For comparison, light takes only 4.5 seconds to circle Earth's equator. These enormous stars are incredibly rare and incredibly unstable. They shed mass through powerful stellar winds, losing material equivalent to Earth's mass every few months. They're also short-lived, burning through their fuel in just a few million years before ending in supernova explosions. When they explode, they might leave behind black holes of dozens of solar masses. The existence of stars this large pushes the boundaries of what stellar physics predicts is possible. Our galaxy contains at least 100 billion planets, and that's a conservative estimate. The Milky Way has between 100 billion and 400 billion stars, and recent exoplanet discoveries suggest that planets are the rule rather than the exception. Most stars have at least one planet, and many have multiple planets. If we assume an average of 1 to 2 planets per star, we get easily over 100 billion planets in our galaxy alone. Many of these are in the habitable zone around their stars, the region where liquid water could exist on a planet's surface. Even if only a small fraction of habitable zone planets actually have conditions suitable for life, and even if only a small fraction of those develop life, and even if only a small fraction of life-bearing worlds develop intelligent life, the numbers are still staggering. In the Milky Way alone, there could be thousands or millions of technological civilizations, or there could be none besides us. The distances are so vast that we might be forever unable to reach each other, even if we're out there in large numbers. The sun's core is the most productive power plant in the solar system, but it's surprisingly inefficient per unit volume. The power density in the sun's core, the amount of energy produced per cubic meter, is only about 270 watts per cubic meter. That's less than the metabolic heat production of a human body per unit volume, and far less than most power plants. A compost heap produces more heat per cubic meter than the sun's core. The sun produces vast amounts of total power, about 3.8 times 10 to the power of 26 watts, but only because it's enormous. The fusion reactions in the core are actually quite slow, with any given proton taking billions of years on average to find another proton and fuse with it. The sun doesn't burn like a fire. It simmers like a slow cooker, sustained for billions of years by its immense mass providing gravitational pressure that maintains the fusion conditions. This slow burn is why the sun is so stable and long-lived, providing consistent energy to Earth for the entire history of life on our planet. Atoms are mostly empty space. If an atom were scaled up to the size of a football stadium, the nucleus would be a marble at the center, and the electrons would be tiny specks orbiting near the stadium walls. The rest is vacuum. You are mostly empty space. The table you're leaning on is mostly empty space. Everything solid you've ever touched is mostly empty space. What we perceive as solid matter is actually atoms held together by electromagnetic forces, with the electron clouds of adjacent atoms repelling each other. When you touch something, you're not actually making contact in the traditional sense. The electrons in your hand's atoms are repelling the electrons in the object's atoms, and you perceive this repulsion as touch. You have never truly touched anything. You've hovered just above it, separated by forces acting across empty space. This is true for every physical interaction in your life. You've never made contact with another person. You've never sat on a chair. You've floated above everything, suspended by electromagnetic forces, never closing that final, infinitesimal gap. If you could see gravitational waves, the universe would be full of ripples. Massive objects moving through space create distortions in space-time that propagate as gravitational waves. Binary systems of black holes, neutron stars, or white dwarfs are constantly generating these waves as they orbit each other. Every galaxy merger produces them. Every spinning neutron star that's slightly asymmetric produces them. The universe is awash in gravitational radiation, waves of space-time curvature passing through everything. These waves are incredibly weak, which is why they're so difficult to detect. The gravitational wave signal from two colliding black holes a billion light-years away changes distances on Earth by less than 1/10,000th the diameter of a proton. But they're real and detectable, and gravitational wave astronomy is now a reality, opening a new way to observe the universe. We're learning to see not just light, but the structure of space-time itself. The quantum vacuum is not nothing, but rather a seething foam of virtual particles. According to quantum field theory, empty space is filled with fields that permeate all of existence. These fields have a minimum energy level, even in their lowest state, and this energy manifests as virtual particle pairs constantly appearing and disappearing. An electron and positron might pop into existence, exist for a tiny fraction of a second, and then annihilate each other. These virtual particles are not directly observable, but they have real effects. They influence atomic energy levels in ways that have been precisely measured and verified. The quantum vacuum is an active participant in physics, not a passive background. Space itself has structure and properties at the quantum level. True nothingness, complete absence of fields and properties, doesn't exist anywhere in our universe. Pulsars are the most accurate clocks in the universe, more precise than atomic clocks. These rapidly rotating neutron stars emit beams of radiation from their magnetic poles, and as they spin, these beams sweep past Earth like a lighthouse, creating pulses we can detect. Some pulsars spin hundreds of times per second with such regularity that they lose less than a microsecond per year. This incredible timing stability comes from their physics. Neutron stars have immense rotational inertia, and there's no friction to slow them down in the vacuum of space. They do slow gradually as they lose energy through radiation, but this slowdown is incredibly regular and predictable. Astronomers use networks of pulsars, called pulsar timing arrays, to search for low-frequency gravitational waves by looking for tiny timing variations in pulsar signals. These cosmic clocks, scattered throughout the galaxy, provide a precise timing network that spans thousands of light years. The observable universe is expanding, but the expansion doesn't affect objects held together by forces stronger than the cosmological expansion. Galaxies aren't expanding, solar systems aren't expanding, atoms aren't expanding. You're not expanding. The space between galaxy clusters is expanding, but within gravitationally bound structures, expansion is negligible compared to the forces holding things together. The Milky Way and Andromeda are actually approaching each other because their mutual gravity is stronger than the expansion rate at their separation. It's only at scales of hundreds of millions of light years, and beyond that expansion dominates. This is because expansion is a very small effect, adding just a bit of extra separation everywhere, and it's only across vast distances that this accumulates into significant velocity. The universe's expansion is real and measurable, but it's also subtle, affecting only the largest scales where no other forces provide cohesion. Every second, billions of neutrinos from the sun pass through your body without interacting. Neutrinos are ghostly particles produced in nuclear reactions in the sun's core. They barely interact with matter, passing through the Earth as if it were transparent. Right now, about 60 billion solar neutrinos pass through every square centimeter of your body every second. Almost all of them pass straight through without touching a single atom. Occasionally, extremely rarely, a neutrino will interact with an atom in your body, but this is so uncommon that you could live your entire life without experiencing even one such interaction. Neutrinos pass through the entire Earth with only a tiny fraction being stopped or deflected. We detect them using massive detectors filled with thousands of tons of water or other materials, hoping that the sheer volume increases the odds of catching a few interactions. Neutrinos are messengers from the sun's core, escaping almost immediately, while photons take hundreds of thousands of years to random walk out to the surface. By detecting neutrinos, we're seeing directly into stellar interiors. The anthropic principle suggests that the universe's properties are constrained by the necessity that it must allow observers to exist. If the fundamental constants of physics were even slightly different, stars might not form, atoms might not be stable, chemistry might not work, and life as we know it couldn't exist. The strength of gravity, the mass of the electron, the strength of the strong nuclear force, all of these seem finely tuned to allow for complexity and life. This raises deep questions. Is this tuning just luck? Are there countless other universes with different constants where life is impossible, and we simply find ourselves in one of the rare universes where conditions permit our existence? Or is there some deeper principle that constrains the constants to life-permitting values? We don't know. The anthropic principle is observation, not explanation. We observe that the universe permits our existence, but we don't know why. This touches on philosophy as much as physics, raising questions about existence, probability, and the relationship between observers and reality. The solar system is moving through the galaxy at about 514,000 miles per hour, but you don't feel it. Just as you don't feel Earth's rotation or its orbit around the sun, you don't feel the solar system's motion through the galaxy. All motion is relative. From our perspective, sitting on Earth, we're stationary, and the galaxy moves around us. But from a galactic perspective, we're racing through space at incredible velocity, orbiting the galactic center about once every 225 million years. This galactic year means that the last time our solar system was in its current position in the galaxy, dinosaurs had not yet evolved. The solar system has completed about 20 orbits since it formed. During one orbit, continents move thousands of miles, species evolve and go extinct, climate systems shift, Earth's position relative to galactic features like spiral arms varies, potentially influencing cosmic ray exposure and other factors that might affect life. We're on a cosmic carousel, spinning through space in multiple nested motions, from Earth's rotation to its orbit to the solar system's galactic orbit to the galaxy's motion through the local group and beyond. The Higgs field permeates all of space and gives fundamental particles their mass. Before the Higgs field was discovered, physicists couldn't explain why particles have the masses they do. The Higgs mechanism provides this explanation. Particles acquire mass by interacting with the Higgs field, with different particles interacting with different strengths, giving them different masses. The Higgs boson, discovered at the Large Hadron Collider in 2012, is a quantum excitation of this field, a ripple in the Higgs field made manifest as a particle. The Higgs field is always there, everywhere, an invisible ocean through which everything moves. Without it, fundamental particles would be massless, traveling at light speed, unable to bind together into atoms. The universe would be unrecognizable. The Higgs field is part of the structure of space-time itself, a background against which all of physics operates. Water on Earth is older than the solar system. The hydrogen in water molecules formed in the Big Bang, but the water molecules themselves formed later. Astronomers have found water in interstellar gas clouds, in protoplanetary disks around young stars, and in comets from the outer solar system. By studying the isotopic composition of water from different sources, scientists have determined that much of Earth's water came from asteroids and comets that formed in the early solar system. But the water in those asteroids and comets predates the solar system itself. The water molecules formed in the interstellar medium, in cold molecular clouds where hydrogen and oxygen combined, before the cloud that would become our solar system even collapsed. When you drink water, you're drinking molecules that existed before the sun, before Earth, floating in the void between stars, eventually swept up in the formation of the solar system and delivered to Earth's surface. Every ocean, every river, every raindrop is older than our world. Black holes eventually evaporate through Hawking radiation, but this process takes an incomprehensibly long time for large black holes. Quantum effects near the event horizon cause black holes to emit radiation very slowly, losing mass in the process. For a black hole the mass of the sun, complete evaporation would take about 10 to the power of 67 years. For supermassive black holes millions or billions of times more massive, the evaporation time is proportionally longer. These timescales are so vast that they're almost meaningless. They're longer than the current age of the universe by factors we can barely express. But in principle, given infinite time, all black holes will eventually evaporate, leaving behind only photons and other particles. This means that even black holes, the most permanent seeming objects in the universe, are temporary. Nothing lasts forever. The universe trends toward increasing entropy, toward heat death, toward a state where all available energy has been dispersed and no more change is possible. Black holes represent concentrations of matter and energy, islands of order in the expanding cosmos, but even they will eventually dissolve. Jupiter's Great Red Spot is a storm that has been raging for at least 400 years and possibly much longer. When telescopes became powerful enough to see Jupiter in detail, astronomers noted this giant red oval in the planet's southern hemisphere. It's been continuously observed since the 1600s, though it may have existed long before humans first saw it. The storm is huge, large enough to swallow Earth several times over, though it has been shrinking in recent decades and is now smaller than it was historically. The storm persists because Jupiter has no solid surface to create friction and no land masses to disrupt atmospheric circulation. On Earth, hurricanes dissipate when they make landfall because friction with the ground and changes in heat and moisture sources weaken them. On Jupiter, storms can persist indefinitely, sustained by heat from the planet's interior and organized by Jupiter's rapid rotation and banded atmospheric structure. The Great Red Spot is a window into atmospheric physics on a scale we can barely imagine, a storm that has outlasted entire civilizations on Earth. The cosmic horizon defines a sphere beyond which we can never see, no matter how long we wait. This horizon exists because the universe has a finite age and light has a finite speed. Light from objects beyond about 46 billion light years, taking into account the expansion of space during the light's travel, cannot have reached us yet. As time passes, this horizon expands, allowing us to see farther. But because the universe's expansion is accelerating, there are galaxies that are currently within our cosmic horizon, but that will eventually cross beyond it, moving away from us faster than light through the expansion of space. These galaxies will fade from view, becoming increasingly redshifted until they vanish from detectability. Future observers, trillions of years from now, will see a much emptier universe than we do, with far fewer galaxies visible. The cosmic horizon is a boundary between the knowable and unknowable, between the observable universe and whatever lies beyond. Time dilation affects astronauts on the International Space Station. Because they're moving fast relative to Earth and experiencing slightly weaker gravity, time passes very slightly faster for them than for us on the ground. Over a 6-month stay on the ISS, an astronaut ages about 0.007 seconds less than people on Earth. This is a tiny effect, but it's real and measurable. If we could travel at speeds closer to the speed of light, the effect would be much more dramatic. At 99% of light speed, time dilation means that 1 year of ship time equals about 7 years of Earth time. At 99.9% of light speed, 1 year of ship time equals about 22 years of Earth time. For the travelers, time passes normally. They don't feel slowed down or experience anything unusual. But when they return home, they've aged less than the people they left behind. This isn't science fiction. It's established physics, verified by experiment, a consequence of the fact that space-time is a unified structure where time and space are interwoven and relative rather than absolute. The asteroid belt between Mars and Jupiter contains millions of asteroids, but the total mass is only about 4% of the Moon's mass. The asteroid belt sounds crowded, and in space movies, ships navigate through dense fields of tumbling rocks. In reality, the asteroids are spread across a huge volume of space, and the average distance between them is hundreds of thousands of miles. If you were flying through the asteroid belt, you'd have to actively seek out asteroids to see them. They'd be tiny dots of light in the darkness, separated by vast stretches of empty space. The asteroid belt is a failed planet, material that never accumulated into a larger body because Jupiter's gravity stirred the region, increasing collision speeds and preventing accretion. The asteroids are leftovers from the solar system's formation, primitive material that has remained relatively unchanged for 4.5 billion years. Studying asteroids gives us insights into the early solar system, showing us the building blocks from which planets formed. Quantum entanglement allows two particles to be connected such that measuring one instantly affects the other, regardless of distance. If you create two entangled particles and separate them, even by billions of light years, measuring the state of one particle instantly determines the state of the other. This seems to violate relativity's prohibition on faster-than-light communication, but it doesn't actually allow you to send information faster than light. The correlations between entangled particles are perfect, but they're also random, and you can't control what result your measurement will produce, so you can't encode a message. Entanglement is real, though, verified by countless experiments. It's one of the strangest features of quantum mechanics, implying that reality at the quantum level is fundamentally non-local, with correlations existing that can't be explained by any local hidden variable theory. Einstein called it spooky action at a distance and was uncomfortable with it, but experiments have confirmed that nature really does work this way. The universe is deeply quantum, and quantum mechanics, strange as it is, accurately describes reality. The coldest temperature possible is absolute zero Kelvin, or negative 273.15 degrees Celsius. At this temperature, atoms would have minimal motion, existing in their lowest possible energy state. But according to quantum mechanics, you can never actually reach absolute zero. The uncertainty principle forbids particles from having both perfectly defined position and perfectly defined momentum, which means they must always retain some motion, some zero-point energy. You can get arbitrarily close to absolute zero, and scientists have achieved temperatures within billionths of a degree, but you can never quite reach it. Absolute zero is a limit, like the speed of light, something you can approach but never attain. Near absolute zero, matter behaves in exotic ways, with quantum effects becoming macroscopic. Superfluids flow without friction. Superconductors conduct electricity with zero resistance. Atoms form Bose-Einstein condensates, quantum states where individual particles lose their identity. These ultra-cold systems let us explore quantum physics on scales we can actually observe and manipulate. The universe is isotropic and homogeneous on large scales, meaning it looks roughly the same in all directions and at all locations. This is called the cosmological principle, and it's a fundamental assumption in cosmology. When we observe the universe on scales of hundreds of millions of light years, the distribution of galaxies is fairly uniform. There's no preferred direction, no special location. We're not at the center of the universe because there is no center. Every point sees roughly the same large-scale structure in all directions. This uniformity is actually quite surprising. Why should the universe be so uniform? The answer lies in cosmic inflation, a period of exponential expansion in the first fraction of a second after the Big Bang. Inflation stretched a tiny, smooth region to enormous size, erasing any large-scale variations that might have existed. The small variations that remain, the tiny ripples in the cosmic microwave background, are quantum fluctuations that were stretched to cosmic scales by inflation. These tiny variations seeded all the structure we see today. The sun is traveling around the Milky Way at about 500,000 miles per hour, but it's also moving up and down through the galactic plane. The solar system doesn't orbit the galactic center in a flat circle. Instead, it follows a wavy path, bobbing above and below the galactic disk like a horse on a carousel. We cross through the galactic plane roughly every 30 million years. Some scientists have suggested that these crossings might correlate with mass extinction events on Earth, as passing through the denser disk exposes the solar system to more gravitational perturbations, potentially sending comets from the Oort cloud toward the inner planets. The evidence for this correlation is debated, but the motion itself is certain. We're not just orbiting the galaxy, we're oscillating through it, our path through space far more complex than a simple circle. Antimatter exists and has been created in laboratories, but it's extraordinarily rare in nature. For every particle, there's a corresponding antiparticle with opposite charge. An electron has a positron. A proton has an antiproton. When matter and antimatter meet, they annihilate each other in a burst of energy. The Big Bang should have created equal amounts of matter and antimatter, and they should have completely annihilated each other, leaving only energy. But obviously, that didn't happen, because we exist, made of matter. There must have been a slight asymmetry, about one extra matter particle for every billion matter-antimatter pairs. That tiny excess is everything we see today. All the stars, galaxies, planets, and people exist because of this mysterious imbalance. Why was there more matter than antimatter? We don't know. It's one of the deepest questions in physics. Some antimatter still exists, created in high-energy processes like certain radioactive decays and cosmic ray collisions in the upper atmosphere. We've even made small amounts in particle accelerators. But bulk antimatter, the stuff of science fiction starship fuel, remains fantastically difficult to produce and store. The Earth's magnetic field has reversed many times throughout history, with north becoming south and south becoming north. These reversals happen irregularly, sometimes a few times per million years, sometimes not for tens of millions of years. The last reversal was about 770,000 years ago. We're overdue for another one by historical standards. Though overdue on geological timescales doesn't mean it will happen soon by human standards. During a reversal, the magnetic field weakens significantly, potentially exposing Earth's surface to more cosmic radiation and solar wind. The field doesn't vanish completely, but it becomes complex and multipolar rather than a simple north-south dipole. Reversals might have affected life on Earth, possibly contributing to evolutionary changes or extinctions by increasing mutation rates from radiation exposure. The magnetic field is generated by convection in Earth's liquid iron outer core, and the physics of this dynamo process allows for these reversals. We can see records of past reversals in rocks, where iron-bearing minerals aligned with the magnetic field when they cooled and solidified, preserving a snapshot of the field's direction at that moment. Light has momentum, and this can be used to propel spacecraft. Photons have no mass, but they carry energy and momentum. When light reflects off a surface, it transfers momentum to that surface, creating a tiny push. This radiation pressure is minuscule, but in the vacuum of space, with no friction to overcome, even tiny forces can eventually accelerate objects to high speeds. Solar sails are a proposed propulsion method that uses large, reflective sails to catch sunlight and radiation pressure from the sun, slowly accelerating spacecraft without needing fuel. The acceleration is gentle, but given enough time, solar sails could potentially reach speeds of tens of thousands of miles per hour or more. Some scientists have proposed even more ambitious concepts, like laser-pushed light sails. A powerful laser array on Earth or in orbit could beam intense light at a sail, accelerating a small probe to a significant fraction of light speed, potentially reaching nearby star systems in decades rather than millennia. These technologies are still largely theoretical, but they demonstrate how light, despite being massless, can interact with matter and produce real physical effects. The moon is geologically dead, with no volcanic activity or plate tectonics. The last volcanic eruptions on the moon occurred about 1 billion years ago. Since then, the lunar surface has been shaped only by impacts from asteroids and comets, and by the slow weathering from micrometeorites and radiation. The moon is too small to retain enough internal heat to drive geological activity. It cooled and solidified, becoming a static world. This makes the moon's surface a time capsule. The footprints left by Apollo astronauts will remain for millions of years, only slowly degraded by micrometeorite impacts. There's no wind, no rain, no geological processes to erase them. The moon preserves its history in a way Earth cannot. On Earth, plate tectonics recycles the crust, erasing the geological record of the distant past. The oldest rocks on Earth are about 4 billion years old. On the moon, rocks from the solar system's formation 4.5 billion years ago still exist, preserved on the surface. By studying the moon, we can learn about the early solar system in ways that would be impossible by studying Earth alone. Voyager 2 has visited more planets than any other spacecraft, flying past Jupiter, Saturn, Uranus, and Neptune. Launched in 1977, It took advantage of a rare alignment of the outer planets to conduct a grand tour of the solar system. The gravitational assists from each planet sped up the spacecraft and changed its direction, allowing it to reach all 4 gas giants with a single mission. The images and data from Voyager 2 transformed our understanding of the outer solar system. It revealed Neptune's great dark spot and violent weather, discovered new moons around the gas giants, showed us the complex ring systems up close, and provided detailed measurements of magnetic fields and particle environments. Like Voyager 1, Voyager 2 is now in interstellar space, sending back data about the boundary between the solar wind and the interstellar medium. Both Voyager spacecraft carry golden records with sounds and images from Earth, intended as messages to any civilization that might find them in the distant future. They're ambassadors from humanity, traveling into an unknown future, carrying our story into the cosmos. Cosmic inflation predicts that our observable universe is just a tiny bubble in a vastly larger multiverse. During the first fraction of a second after the Big Bang, space underwent exponential expansion, growing by a factor of at least 10 to the power of 26 in a period of about 10 to the minus 32 seconds. This inflation solved several problems in cosmology, explaining why the universe appears so uniform and flat. But inflation, once it starts, may be eternal in some regions. While inflation ended in our bubble, creating the Big Bang as we understand it, in other regions of space, inflation continues, and new bubble universes constantly form. Each bubble might have different physical constants, different particle physics, different rules. This eternal inflation scenario suggests a multiverse of staggering size and diversity, with our entire observable universe just one bubble among countless others, forever separated from each other by exponentially expanding space. This is speculative, but it's a logical consequence of our best theories about the early universe. We may never be able to test these ideas directly, but they represent the cutting edge of theoretical cosmology. The speed at which Earth orbits the Sun is about 67,000 miles per hour. You're traveling through space at this speed right now, orbiting the Sun along with everything else on Earth. The Sun's gravity holds Earth in orbit, providing the centripetal force that keeps us falling around the Sun rather than flying off into space. If Earth suddenly stopped moving, it would fall straight into the Sun, plunging inward in a death spiral, taking about 65 days. If Earth suddenly sped up beyond a certain velocity, it would escape the Sun's gravity and drift into interstellar space. We're balanced at exactly the right speed to maintain a stable orbit, a speed determined by our distance from the Sun and the Sun's mass. All the planets maintain similar balances, each orbiting at the speed required for its particular distance. This orbital mechanics, described by Newton's laws and refined by Einstein's general relativity, governs the motion of everything from planets around stars to stars around galactic centers to galaxies around each other. Red giants are stars near the end of their lives, having exhausted the hydrogen in their cores. When the core hydrogen runs out, fusion stops, and the core contracts under gravity, heating up. This heat causes hydrogen in a shell around the core to begin fusing, and the energy from this shell burning causes the star's outer layers to expand enormously. The star becomes a red giant, cool on the surface, but huge in size. Red giants can be dozens or hundreds of times larger than they were as main sequence stars. Betelgeuse, a red supergiant in the constellation Orion, has expanded so much that if placed at the center of our solar system, its surface would extend past the orbit of Mars. Red giants are dying stars, but their death throes can last hundreds of millions of years. Eventually, they'll shed their outer layers, creating beautiful planetary nebulae, and leave behind white dwarfs, the dense cores of the original stars. Our sun will become a red giant in about 5 billion years, expanding to perhaps 100 times its current size, likely engulfing Mercury and Venus and making Earth completely uninhabitable. Gravitational lensing allows us to see galaxies that would otherwise be too distant and faint to detect. When light from a distant galaxy passes near a massive object like a galaxy cluster, the massive object's gravity bends the light, acting like a lens. This can magnify the background galaxy, making it brighter and more visible. In some cases, lensing creates multiple images of the same background galaxy, seen around different sides of the lensing object. The most dramatic lensing events create Einstein rings, where the background galaxy is directly behind the lensing object, and its light is bent into a complete ring around the lens. Gravitational lensing is not just beautiful, it's useful. By studying how light is bent, we can map the distribution of matter in the lensing object, including dark matter that we can't see directly. Lensing reveals that galaxy clusters contain far more mass than we can account for with visible matter, providing some of the strongest evidence for dark matter's existence. Lensing also lets us see some of the most distant galaxies in the universe, galaxies that formed when the universe was young, magnified by foreground galaxy clusters into visibility. The speed of sound in space is meaningless because space is essentially a vacuum and sound requires a medium to travel through. Sound is a pressure wave moving through matter, whether air, water, or solid material. In the vacuum of space, there's no medium for sound waves to propagate through, so there's no sound in the conventional sense. However, plasma, hot ionized gas, can support pressure waves, and these can be converted into audible sound through data processing. Astronomers have done this with data from various sources, creating sonifications of astronomical phenomena. The sound waves in the early universe that seeded galaxy formation, the oscillations of stars detected through asteroseismology, the electromagnetic waves from planets and moons, all of these have been converted into sound humans can hear. These sonifications aren't what you would hear if you were there, because you wouldn't hear anything, but they represent real physical waves translated into a form we can perceive. Space may be silent in one sense, but it's full of vibrations and waves in another. Rogue black holes might be drifting through the galaxy, invisible and nearly impossible to detect. When massive stars go supernova, if the explosion is asymmetric, the resulting neutron star or black hole can receive a kick, accelerating it to high velocity. Some neutron stars are observed moving at hundreds of kilometers per second, and black holes could receive similar kicks. A stellar mass black hole traveling through space would be dark, emitting no light, detectable only by its gravitational effects. If a rogue black hole passed through a stellar neighborhood, it could gravitationally disturb planets and comets, potentially sending objects hurtling out of their systems or changing their orbits dramatically. If a rogue black hole passed close to our solar system, it could perturb the Oort cloud, sending comets raining toward the inner planets. We wouldn't see it coming unless it passed very close to a star and created detectable lensing or accretion effects. The likelihood of such an encounter is very small. The galaxy is vast and black holes are rare and small, but it's not impossible. There could be black holes wandering through the galaxy, invisible predators in the darkness between stars. The cosmic microwave background has tiny temperature variations of about 1 part in 100,000. These variations represent quantum fluctuations in the early universe that were stretched to cosmic scales by inflation. Regions that were slightly denser became the seeds for galaxies and galaxy clusters. Regions that were slightly less dense became voids. By studying the pattern of these temperature fluctuations, cosmologists can learn about the conditions in the early universe, the composition of matter and energy, the geometry of space, and the nature of inflation. The cosmic microwave background is the oldest light we can see, a snapshot of the universe at age 380,000 years before stars or galaxies existed. It's remarkably uniform, which tells us the universe was remarkably smooth at that early time. The tiny variations that do exist are precious information, encoding the initial conditions from which all structure grew. Different theories of the early universe predict different patterns of variations. So by measuring the CMB precisely, we can test these theories and constrain our models of cosmic evolution. The emptiest places in the universe are the cosmic voids, vast regions of space with very few galaxies. These voids can be hundreds of millions of light years across, containing only scattered galaxies in regions where galaxy clusters and filaments would normally have dozens or hundreds. Voids aren't completely empty. They contain dark matter and diffuse gas, but they're remarkably underdense compared to average cosmic density. Voids exist because structure formation is a runaway process. Dense regions attract more matter, becoming denser, while underdense regions lose matter to their surroundings, becoming more empty. The cosmic web structure of filaments and voids emerged naturally from this process. Galaxies that do exist in voids are often unusual, having formed in isolation without the gravitational interactions and mergers that shape galaxies in denser regions. Studying void galaxies gives us insights into how galaxies form and evolve in different environments. Every star you can see in the night sky with your naked eye is in the Milky Way galaxy. Even the most distant stars visible without a telescope are only a few thousand light years away, tiny fraction of the Milky Way's 100,000 light-year diameter. The Andromeda Galaxy, our nearest large galactic neighbor, 2.5 million light-years away, appears as a faint smudge to the naked eye, too distant for individual stars to be resolved without powerful telescopes. When you look at the night sky, you're seeing your local cosmic neighborhood, the stellar suburbs of our position in the galactic disk. Everything you see is relatively close by astronomical standards. The vast majority of the universe is invisible to the naked eye, visible only through telescopes that can gather more light than our eyes and that can observe at wavelengths we can't perceive. Ancient humans saw essentially the same stars we see because the stars visible to the naked eye are close enough that their proper motion, their actual movement through space, is imperceptible over human timescales. The constellations appear fixed, though over tens of thousands of years, they do slowly change shape as stars move relative to each other. Titan, Saturn's largest moon, has a thick atmosphere and liquid methane lakes on its surface. It's the only moon in the solar system with a substantial atmosphere, and it's the only place besides Earth where we've confirmed stable liquid on the surface, though Titan's lakes are methane and ethane rather than water. Titan's atmosphere is mostly nitrogen, like Earth's, but it's denser and the surface pressure is about 50% higher than Earth's at sea level. The temperature is extremely cold, around minus 179 degrees Celsius, cold enough that water ice is as hard as rock and methane exists as liquid. Titan has a methane cycle analogous to Earth's water cycle, with methane rain, rivers, lakes, and possibly underground reservoirs. The Cassini mission studied Titan extensively, even landing the Huygens probe on its surface, revealing a complex, dynamic world with organic chemistry occurring in the atmosphere and on the surface. Titan might have a subsurface ocean of liquid water beneath its icy crust, potentially making it a target in the search for life. The combination of organic chemistry and possible liquid water makes Titan one of the most intriguing moons in the solar system. Dark energy makes up about 68% of the universe's total energy, but we have no idea what it is. We observe its effects through the accelerating expansion of the universe, but we don't know what causes it. The simplest explanation is that dark energy is a property of space itself, a cosmological constant representing the energy of the vacuum. But we don't know why the vacuum would have this energy or why it has the specific value we measure. The cosmological constant problem is one of the biggest unsolved problems in physics. Quantum field theory predicts a vacuum energy, but the predicted value is about 120 orders of magnitude larger than what we observe. That's not a small discrepancy. It's the worst prediction in the history of physics. Yet something is driving the universe's accelerated expansion, and we call it dark energy even though we don't understand it. Dark energy determines the ultimate fate of the universe. If it remains constant, the universe will expand forever, eventually reaching a cold, dark state of heat death. If dark energy strengthens over time, expansion could accelerate catastrophically, eventually tearing apart galaxies, stars, planets, and even atoms in a big rip. We're observing the universe to try to understand dark energy better, but it remains deeply mysterious. And so we spiral back once more through these cosmic scales and mysteries. You've traveled from the smallest quantum fluctuations to the largest structures in the universe, from the briefest moments after creation to the unimaginable timescales of the deep future. You've seen how matter and energy dance together, how space and time are woven into a unified fabric, how gravity shapes the cosmos from planets to galaxy superclusters. You've confronted the limits of human knowledge and the vast territories of our ignorance. We know so much, and yet what we know only illuminates how much more there is to discover. The universe is not just vast in space, but vast in possibility. Every star represents potential worlds. Every galaxy contains billions of these possibilities. The observable universe, with its hundreds of billions of galaxies, contains more possibilities than we can count or imagine. Somewhere out there, perhaps, other minds are looking up at their night sky and wondering the same questions you're wondering now. Are we alone? What does it all mean? Why does anything exist at all? We don't have final answers to these questions. We may never have final answers, but we keep looking, keep questioning, keep pushing the boundaries of our understanding. That's what makes us human, that drive to know, to understand, to find meaning in the vastness. You are part of this great human project of understanding the cosmos. By learning these facts, by contemplating these mysteries, by allowing yourself to feel wonder at the scale and complexity of existence, you're participating in something profound. The universe is old beyond comprehension, vast beyond measure, and strange beyond imagination. And yet here you are, conscious and aware, able to contemplate it all. You are made of the cosmos, and the cosmos is experiencing itself through you. In this moment, the universe is awake and wondering. That's beautiful. That's mysterious. That's enough. Rest now, cosmic wanderer. Let the universe continue its slow dance while you sleep. The galaxies will keep turning. The stars will keep burning. Space will keep expanding. It will all be here when you wake, waiting for you to look up once more and wonder. Close your eyes and drift, knowing that you are home, you are safe. You are a temporary pattern in the eternal flow of cosmic energy. Here for a moment, precious and beautiful and brief. Sleep well, stardust. Sleep well. Number 50, incredible facts about the universe that will blow your mind. And so we return again to our starting point. Here you are, in your particular location, at your particular time, made of atoms forged in stars, living on a planet orbiting a star in a galaxy among countless galaxies in an expanding universe whose ultimate origin and fate remain mysterious despite all we've learned. You've journeyed through cosmic scales, from the quantum foam to the largest structures, from the briefest moments after the Big Bang to the incomprehensible timescales of the far future. You've seen the universe as physics describes it, vast, ancient, strange, beautiful, and indifferent to human concerns, yet somehow, improbably, capable of producing human consciousness. Take a breath. Feel the air entering your lungs, oxygen created in stars, nitrogen from supernova explosions, molecules older than Earth. Feel your heart beating, your blood flowing, complex chemistry making possible the improbable persistence of your existence. You are here now, alive and conscious, able to contemplate the cosmos and your place in it. This is remarkable. This is profound. You are a way for the universe to know itself. And in this moment, the universe is paying attention. The universe will continue long after you're gone. Stars will form and die. Galaxies will merge. Space will expand. The story will unfold across timescales that dwarf human history. But right now, in this moment. You are here to witness it, to wonder at it, to try to understand it. That's beautiful. That's enough. Sleep now, under your patch of sky on your spinning planet, in your solar system, in your galaxy, in your observable universe. Let these thoughts settle like cosmic dust, slowly drifting, finding their place among your other memories and knowledge. The universe is waiting, patient and eternal, for you to wake and wonder again. Rest easy, cosmic traveler. You are home, and home is everywhere.